Okay, in this video we are going to do practice antiderivatives or integrals for the AP Calculus A, B, or BC exam. So these are the types of integrals that everybody should know going into the exam. There's a couple of additional things that if you're taking the BC exam you should know. We're not going to cover them in this, so that this is like an all-purpose video. Let's see, what's in this? So I'm going to do 40 problems that are based on actual problems from AP exams. So I was looking through practice tests, exams that have been given in previous years, and I wrote these problems based on those. I'm going to give you general tips as we go along, and then I'm going to also tell you things that you definitely need to have memorized if you're going to be successful doing these kinds of antiderivatives. There's a link to the problems in the description, so if you want to get those and try them on your own and then watch with me, or just scroll through and see what I got as solutions, up to you how you want to deal with it. Also, I kind of fully expect people to bounce around as they're doing this. So let's get started. It's probably going to be a long video. All right, the first one we're going to do is the integral of secant times tangent dx. So you need to memorize the derivatives of the trig functions, because if you don't have the derivatives memorized, you're not going to recognize them to find the antiderivatives. So derivative of sine is cosine, cosine is negative sine, tangent is secant squared, cosecant is negative cosecant cotan, secant is secant tan, and the derivative of cotan is negative cosecant squared. So of the things to memorize there, they're all super important, but one thing that you really want to notice is that the derivatives of all the cofunctions are negative. That's going to be super important. In general, it's not important for this problem, because for this problem, I'm trying to integrate secant tan, and since I memorized the derivatives, I know the derivative of secant is secant tan. The antiderivative of secant tan is going to be secant of x, and then plus c. We're not going to forget plus c the entire way through. So plus c on everything. So you're going to memorize the derivatives. Having the derivatives memorized will allow you to recognize the derivatives so you can find the antiderivatives. So make sure you have those memorized. That's a good start to being very successful. All right. Our second thing, integral of secant of 2x tan of 2x dx. All right, what is going on here? This is basically the same problem, except we definitely need to know u-substitution. And as we're using u-substitution, the most common mistake that I see people make is they forget to sub for dx, right? Everything in your new integral has to be a u, including that dx has to become du. So let's see how we do this. First, I'm going to look through and try to identify u. It's usually something in parentheses. Because I know secant tan is the derivative of secant, I'm looking at this and saying u is equal to 2x. It's often the argument of the trig function. So I'm going to let u equal 2x. Throughout the video, I'm going to try to do all of the work. A lot of you are probably at the point where you're doing this in your head. That's fantastic. You can scroll through and find the answer, or you can see how I'm doing the work. It's up to you, but I'm going to do the work. So 1/2 du is equal to dx. So what's really happening there is du is equal to 2 dx, and then I'm dividing both sides by 2 because I want to substitute just for dx. So I have secant of u, tan of u, and now I need to substitute for dx, and dx is 1/2 du. I'm going to pull the 1/2 out as a constant multiple, so 1/2 and du. All right, this is our integral, but we know that secant u, tan u, du, the integral of that is just secant of u, so I'm going to get 1/2 secant of u plus c. The original integral was in terms of x, not in terms of u, so we have to go back to our x values, but we know that u is equal to 2x. So 1/2 secant of 2x plus c. All right, moving on to the next thing. We want to do the integral of t squared minus 3 to the t. So that's an exponential function, and then dt. All right, this one's really important. It's overlooked. It's not as common as the other things, so I understand why people don't remember it as well. But you really need to remember the derivative of a to the x, so a constant raised to the variable power, is a to the x natural log of a. The most common exponential that you integrate is e to the x, and the integral of e to the x, integrate or take the derivative of, but the most common one is e to the x. The derivative of e to the x is e to the x. The reason it feels like that's not matching this is that e to the x times the natural log of e, the natural log of e is 1, so we always simplify that. But when it's more general and it's a to the x, you have to have a to the x natural log of a. That's going to be really important to know because we're going to do a substitution, and if we don't know the derivative of 3 to the t, how are we going to do that? So I'm going to break this into two integrals. I'm going to make it t squared dt minus the integral of 3 to the t dt. All right. The first integral, we're just reversing the power rule, so I'm going to do plus 1 times the reciprocal. So 1/3 t cubed. I'm going to hold off on plus c until like the very end. Now I need to do this other integral, right? So I'm going to let u equal the entire exponential. I'm going to let u equal 3 to the t. That's going to be a tip that I write down later. I don't know why I didn't write it down here, but I'm going to let u equal 3 to the t. Anytime you're integrating an exponential, let u equal the entire exponential. So I'm going to let u equal 3 to the t. Then, because I know the derivative of 3 to the t, I can say du is 3 to the t, natural log of 3 dt. From here, I'm going to say 1 over the natural log of 3 du is 3 to the t dt. Why am I choosing that? Well, because I have 3 to the t dt in my original integral, so actually I can sub for 3 to the t dt. If you're doing an exponential and u-substitution is going to work, you are always going to end up with like some constant multiple times the integral of just du. That will always happen. We'll see that throughout the video. So I'm going to make this like minus 1 over the natural log of 3 du, right? Because 3 to the t dt is 1 over the natural log of 3 du. That's our integral. And that integral of du, that will happen with every exponential. I'm going to repeat myself like a million times in this video. I can already feel it. All right, so we got 1/3 t cubed minus 1 over the natural log of 3. And then u is the variable, right? So we're integrating du. U is the variable, so the integral of 1 will become u. It'll become whatever the variable was, right? The same as when you integrate dx, you get x. If you integrated dz, you would get z, because the derivative of x with respect to x is 1. The derivative of u with respect to u is 1. The derivative of, I don't know, z with respect to z is 1. We're integrating 1. We're going to get the variable, and the variable is u. So I don't know if I hammered that home enough. I hope so. Plus c, because every time. And then we just go back and sub in. So 1/3 t cubed minus 1 over the natural log of 3. We know that u is actually 3 to the t. So 3 to the t and plus c. All right, good deal. Let's take a look at our next one. So this one is really similar actually, except instead of having 3 to the t, we have e to the 3x over 2, which is fine. So we want the integral of 4 minus e to the 3x over 2 dx. You should definitely memorize. I mean, I'm sure you do have this memorized because this is fundamental. You have to memorize the derivative of e to the x is e to the x. And because it just comes up all the time, the integral or the antiderivative of e to the x dx is e to the x plus c. That's going to come up a ton, and we're going to make use of it all the time. So I'm going to do the same thing I did last time and break it into two integrals. You might be at the point where you just do the integral of 4 is immediately 4x, and you just kind of like move on with that. That's totally fine. That's probably what I would do. But I'm doing this so that someone who is practicing for the AP exam knows all the work they would need to show in the event that they needed to show work. So I get this. I'm going to integrate that first integral to just get the 4x minus, all right, we have an exponential. If I'm integrating an exponential, I let u equal the entire exponential. So I'm going to let u equal e to the 3x over 2. Now I'm going to find du, should be e to the 3x over 2 times 3 halves, right? Chain rule, and then dx. So you really, it's kind of interesting. When you start learning antiderivatives, you get better at derivatives because like half of doing an antiderivative is matching up du, which means taking a derivative. So the chain rule has come into play here, right? E to the u, the derivative of e to the u is e to the u du. So e to the 3x over 2 will be e to the 3x over 2 times 3 halves. So this is what we have. Look at the original and you see that you see e to the 3x over 2 dx. So I'm going to multiply by 2/3 on both sides so I can perfectly match what I have. So I'm trying to match the original integrand was e to the 3x over 2 dx. So to get rid of that 3/2 on the right-hand side, I multiply both sides by 2/3. All right, now we're going to sub in. So this becomes 2/3 the integral of du. Every time with an exponential, if you let u equal the exponential, you're going to end up with the integral of du 100% of the time. So let's do this. 4x minus 2/3. We had that long conversation about why you get u when you integrate this. So we're going to just go with u plus c. And then we know what u is. U is e to the 3x over 2. So we get 4x minus 2/3 e to the 3x over 2 plus c. All right, so what's the takeaway? This is the tip that I should have written for the previous problem. If you're integrating an exponential, let u equal the exponential, and you will be successful as long as you can remember how to find the derivative of an exponential so that you can figure out du. So make sure you know all of these things, right? You're going to take the AP exam and you want to be successful. Let's take a look at another one. So this one, I don't know. When I was making the video, I'm not sure this isn't a typo in the problem, but like we can still do it. It's just, this feels harder than maybe it should be to begin with. But let's see what we can do. We're going to integrate e to the radical 3x over radical 2x. That radical 2x is super annoying to me. But we're integrating an exponential, so I'm just going to let u equal the exponential, right? That's the rule that we're going to try to follow there. I am, because I don't want to take the derivative the way it's currently written, I'm going to rewrite this a little bit. And I will do this all of the time with a product inside a radical. I'll make, radical 3x is just radical 3 times radical x. And then I would prefer rational exponents when I'm taking derivatives or antiderivatives. So I make radical x to the 1/2. And then from here, we can find du. Don't forget the chain rule. So we get e to the u, and then the derivative of u is just root 3, and then 1/2 x to the negative 1/2 dx. All right, so what do we have in our original? Well, that radical 2x is bothering me. I'm definitely going to do like 2 over root 3 to just get the exponential by itself, right? And then I have a, what do I have here? I have I've multiplied both sides by 2 over root 3, and I rewrote the right-hand side. So let me talk my way through that. So multiply by 2 over root 3. So I get 2 over root 3 du equals e to the root 3 times x to the 1/2. That's just there. I made x to the negative 1/2 into 1 over x to the 1/2, but I rewrote that as a radical because I'm trying to match the integrand, and then dx is there. This root 2x is a problem. It's not really a problem, but root 2x is root 2 times root x. So I'm going to take advantage of that before I even do anything and just factor that 1 over root 2 out and have this thing. Because when we're doing u-substitution, we're obsessed with matching the integrand. That's what we need to do. And so now this and this are exactly the same. So we just have this weird factor of 1 over root 2 hanging around. All right, we replace the whole integrand with our constant multiple integrand of du. Going to happen every time. And then we integrate du to just get back to u. So I'm getting 2 over root 6, because root 2 times root 3 is root 6. And then u plus c. We know that u is e to the root 3 times x to the 1/2. This one's a doozy, man. And then plus c. All right. Now, I will tell you there's an alternate version of this where you just rationalize that 2 over root 6, right? Multiply the top and the bottom by root 6. That'll give you, I'm not going to make you watch that, root 6 over 3 e to the root 3x plus c. If it's multiple choice, who knows? That might be what it looks like. This one's a little harder than I think you would see on the AP exam. I don't think they would do that root 2x thing to you. I think they would probably just make it root x, or they might make it root 3x. I think I have a typo where I just made it root 2x, but we can still do it, so not a problem. All right, let's move on to number 6. All right, integral of 2 sine of 3x dx. This one is just straight. I'm going to rewrite the integral where I take out 2 because constant multiples, you basically ignore them until the end, then just multiply them back in. u is going to be 3x. It's almost always the argument of the trig function. So that means that 1/3 du is dx because du equals 3 dx, and I divide by 3. So let's just substitute and do it. So we get 2. I'm going to have dx is 1/3 du. So I'm going to pull out the 1/3. So 1/3 integral of sine of u du. All right, and then we just have to integrate this. We memorized all of the derivatives of the trig functions. We know the derivative of cosine is negative sine, which means the antiderivative of sine should be negative cosine. We're going to pick up a negative here. So we'll get negative 2/3 cosine of u plus c. All right, and then we're going to sub back in for u because the original had x's, not u's. It's actually a really common mistake to forget to substitute back in. And here's the tip. If the integral ends up a co-function, so cosine, cosecant, cotangent, don't forget that you have to multiply in a factor of -1. Doesn't mean your answer will be negative, because if there's another negative hanging around, you'll get like negative times negative. But if you do the integral of sine to get cosine, you actually get negative cosine. Anytime you end up with a co-function, you have to multiply in a negative. And that's another like common thing that I see people do wrong, which is why it's one of the tips. All right, let's try number 7. The integral of x root 36 minus 4x squared dx. When you're not so I mean, if you're not sure how to do this, I would initially think a thing inside a radical is a really good choice for you because it'll make the problem look simpler. Root 36 minus 4x squared looks crazy. Root u, the square root of u, doesn't look as crazy. And often with u-substitution, that's what you're doing. Just try to make the problem look simpler. So I'm going to let u equal 36 minus 4x squared. And if it works, it's going to work. If it works, good. If it doesn't work, try a different value for u. That's one of the things when people are first learning to do antiderivatives. They're really hesitant to just like dive in. You actually just have to dive in. Choose a u, see if it works out. If it does, you're good. If it doesn't work out, choose a different u. It doesn't mean you're doing it wrong. It just means you're like feeling your way through the problem. So here du is going to be negative 8x dx. So negative 1/8 du is going to be x dx. And this is good because I actually, in the integral, have an x dx, right? Which means I can just make all of that, the x dx, into negative 1/8 du. Let's do our substitutions. I don't even remember if I read this problem. It's the integral of x root 36 minus 4x squared dx. Anyway, we sub in for x dx, we get negative 1/8 du. Then this will become u to the 1/2 du. Remember, radicals are like the enemy of success in calculus. You got to change them into rational exponents as soon as possible. All right, we're going to reverse the power rule. So negative 1/8 plus 1 times the reciprocal. So 1/2 plus 1 is 3/2. So 2/3 u to the 3/2. And then plus c. And then we are going to sub back in. So I'm adding, I get negative 2 over 24 is negative 1/12. And then u is 36 minus 4x squared to the 3/2 plus c. So I'm perfectly happy with this answer. Free response, I definitely leave it. If it's multiple choice, you might have to match the answer, and there is an alternative version of this answer. I'm just going to like show it, and if you want to follow along, you can pause and read through what I did. The alternative version looks actually pretty different. Negative 2/3, the quantity 9 minus x squared to the 3/2 plus c. And you can see the arithmetic or the algebra, I guess, I don't know which one that is, that I did to make that. So I've got a tip for you on this one, which we discussed already. If you are not sure what to make u, you should try things that are in parentheses, things that are inside radicals, and in general, the denominator of a fraction is a really good choice for you. None of those will work 100% of the time, but that's kind of like when you're thinking, oh my God, I don't know what to try. You do have ideas of what to try. Try things that are in parentheses, things in radicals, and denominators. And that'll get you started, and starting is really the essential thing. All right, next problem. Remember, you can take a break if you want. You don't need to go all the way through this. We're approaching 20 minutes, and we are like 1/5 of the way through, so that's nuts. Let's see what we got. All right, integral of cosine of pi over 5 t dt. So this is a straight u-substitution problem. Many of you, I think, will probably be doing this in your head by the time you're taking the exam, and that's outstanding. Never hurts to do the work, though. So du is going to be pi over 5 dt, which means that 5 over pi du is equal to dt, and we're going to direct sub for that. So we will get dt is 5 over pi du, so I'm going to take out the 5 over pi. It's interesting, like, you kind of substitute for dx or dt or d whatever, the original differential. You kind of substitute for that before you make other substitutions because you often are pulling out a constant multiple. It's normal. You get used to it. All right, so I know the derivative of sine is cosine, so this is looking good. 5 over pi, and then sine of u plus c, and then we sub back in. And we get 5 over pi sine of pi over 5t plus c. There we go. All right, that one's, maybe our I don't want to say simplest. It wasn't simple, but the most straightforward one that we've done in a while. All right. Integral of x squared e to the 4x cubed dx. I see an exponential function, and I'm going to follow my own rule. I'm going to let u equal the exponential. So if you are doing that, you will probably be successful. Certainly on the Calc AB and BC exams, that's almost certainly going to work out for you. So du, we need to remember the chain rule, e to the 4x cubed times 12x squared dx. Then we just compare, right? We have x squared, we have e to the 4x cubed, and we have dx. So I'm going to divide through by 12. That's the most common thing to do, is to take the constant multiple over to the other side. So I get 1/12 du. I have this, I have this, I have this. So this integral just becomes 1/12 the integral of du. As I mentioned, when you make u equal the exponential, if it's going to work out, you end up just integrating du every time. So this will give us 1/12 u, and then plus c, and then we sub back in because the original did not have u. All right, let's take a look at number 10. So we want the integral of dx over 6 minus 7x. Here's another thing that you should have memorized. You definitely want to memorize this. The derivative of natural log of x is 1 over x. So there's two things to memorize here, right? With the derivatives of the trig functions, I said just memorize the derivatives of the trig function so you can recognize the derivatives and go backwards. The derivative of natural log of x is 1 over x. Technically, x is greater than 0, but usually we don't write that and worry about it here. The integral of 1 over x is the natural log of the absolute value of x plus c. So you're never going to forget plus c on an integral. You're also never going to forget the absolute value around the argument of natural log. You can't afford to forget it. That's like a basic, simple, free point. Don't do it. All right. With that in mind, I see a fraction. I don't know what else to do. I'm going to let u equal the denominator. So 6 minus 7x, which means that du is negative 7 dx, which means negative 1/7 du is dx. All right, and we're ready to sub in. So I'm going to sub for dx. It's negative 1/7 du. So negative 1/7 du, the denominator is u. All right, this is, because we just talked about it, this obviously matches the derivative of natural log. So we need to find the antiderivative of this, and don't forget the absolute value. So it'll be the natural log of the absolute value, which I'm going to try to put the absolute value in red every time throughout the video because it's that important. And then we just sub back in. So negative 1/7, natural log, absolute value, 6 minus 7x plus c. All right, so what is the tip here? The tip here, we didn't really run into it, but if you use u-substitution and it leads you to the integral of u to the negative first du, which this did. Look at that first step. We got negative 1/7 the integral of du over u. If you're in the mindset of reversing the power rule, you would rewrite that as u to the negative first and then do plus 1 times the reciprocal. But negative 1 plus 1 is 0. The reciprocal of 0 is 1 over 0, doesn't even exist. Now you're kind of in trouble, except you're not, because every time that happens to you, you actually have a natural log. So when you're reversing the power rule and it fails, it makes you divide by 0, you definitely have a natural log. And you just want to kind of remember that. So I'm going to like actually in the real world pause here and come back and finish this. But you just heard probably my voice crack. I'll be back, but you're just going to keep watching. So this doesn't really even matter to you. I'm just letting you know I'm taking a break. So if I sound different or something when I come back to do problem 11, that is why. All right, I'm back. Let's do number 11 here. So we got the integral of 4t cubed minus 3t squared plus 2 dt. So remember, the dt is telling you the variable is t, but you can see that the variable is t. And so this one's pretty straightforward. So I'm just going to reverse the power rule all the way through this thing. So we're going to do plus 1 times the reciprocal. So we get t cubed goes to 1/4 t to the 4th. Constant multiples are just there. You save them till the end, then you deal with them. You might have just written t to the 4th on that one. Also fine. Same thing's going to happen here, right? So it's minus 3/3 t to the 3rd plus 1 times the reciprocal. So when I say plus 1 times the reciprocal, I'm saying plus 1 to the exponent times the reciprocal of that new exponent. So 2 becomes 3, the reciprocal is 1/3, and then the integral of 2 will be 2t because dt tells us t is the variable, plus c, and then we would want to simplify this to t to the 4th minus t cubed plus 2t plus c. And the tip for this would be definitely check reversing the power rule by using the power rule, right? Like it's easy enough to check your antiderivatives by taking the derivatives. So you should definitely do that. There's no excuse not to do that. All right, let's look at number 12. Number 12 is like a rerun of a previous problem. You might be able to do this in your head at this point. So it's the integral of 4t to the 5th minus 5 to the t. So 5 to the t is an exponential, right? So when we do the substitution, we'll let u equal 5 to the t. But let's see if we can do this kind of like in our head, right? So I have 4t to the 5th. I'm going to do plus 1 times the reciprocal. So plus 1 to the exponent is 6. The reciprocal is 1/6. So I have 4 1/6. That's 2/3. And then t to the 6th. And then what I'd want to do from there is now I have to integrate negative 5 to the t. I have a lot of trouble saying that for some reason. I guess because you say 5t way more often, but negative 5 to the t. So there should have been a natural log of 5, so I will need a 1 over natural log of 5, and then it'll just be 5 to the t. So negative 1 over natural log of 5, 5 to the t, and then plus c. If you're not into doing them in your head, that's totally fine. I'm about to do all of the work. But I wanted you to know that, like, yes, you can be doing some of these in your head, and that's totally fine. So what I'm going to do to show the work is break this thing into 2 integrals. I'm going to pull that 4 out as a constant multiple. And then I'm just going to, on the first one, reverse the power rule as discussed. So we'll get 4 over 6, t to the 6th. And then here, we're going to do a u-substitution. I'm going to let u equal the entire exponential, because that's what we do. I'm going to remember how to find the derivative of 5 to the t, because if you don't know the derivative, you're going to have trouble finding the antiderivative. So this will give us 5 to the t, natural log of 5 dt. Divide through by the natural log of 5 because we don't have that in the original. We just have 5 to the t dt. And then every time when you're doing an exponential, if you do this process, you end up integrating just like a constant multiple of du. So this will become perfect. We got 1 over the natural log of 5, we pull out as a constant multiple, du, and we can integrate this. So 4/6 becomes 2/3, and 1 over the natural log of 5, and then u plus c. We know u is 5 to the t. So here we go. 2/3 t to the 6th minus 1 over natural log of 5, 5 to the t plus c. All right, let's move on to number 13. So we are going to integrate. So this one, again, it's dx over 3x plus 2. Feels like natural log to me, right? That's just like 1 over something. And so if you just have like 1 over a linear function, it's going to be natural log basically every time. If you're not sure what to do on a problem like this, we have a fraction. And so I'm going to let the denominator equal u and kind of go from there. So as you do more of them, you start to recognize them, and that's really the key. When people are super fast at these, it's that they've done a lot and they recognize what's going on. So 1/3 du is dx, because really it's du is 3dx, and then we divide by 3. We're going to substitute for dx, and here we go. So you immediately pull out the 1/3. You get the integral of du over u. Perfect. So this will be 1/3 the natural log of the absolute value of u, right? We're putting in red because it's super important and you can't forget it. And then we'll just sub back in. So 1/3 natural log absolute value of 3x plus 2, and then plus c. All right, not bad. Let's take a look at the next problem. So this type of problem can look really intimidating when you haven't yet kind of like grasped how u-substitution helps you out. So we're going to do the integral of sine to the 7th of 5x times cosine of 5x dx. What you might choose to do on this problem, because initially it's like, what do I let u equal? Well, usually u is the thing to the highest power, which in this case is, so in my list of things I look for u, I had things in parentheses, things in radicals, things in denominators. If there's a bunch of stuff in parentheses, it's usually the thing to the highest power. And in this case, I'm going to rewrite this just so it looks a little clearer. And you might find yourself doing this, and that's totally fine, right? Like, don't let someone tell you that the work you're doing is too much work if that work is working for you. So I have rewritten this, and now it's pretty clear to me the thing to the highest power is sine of 5x. So that's what I'm going to go with. U is equal to the sine of 5x. Now, you might be worried about that cosine of 5x, but once you've chosen u, you have to hope, well, if it's going to work, you have to hope that everything else is just a part of du. So let's find du. du is cosine of 5x times 5 by the chain rule, and then dx. So 1/5 du is going to be cosine of 5x dx, and this is perfect, right? So you have to have that faith that it's going to work out, and in Calc AB, it's pretty much always going to work out. In Calc BC, it's going to work out like 90% of the time. There's a couple other techniques you need to know in there. But we're going to do our substitutions. So that all is going to be 1/5 du. So we'll start with pull out the 1/5. Because remember I said you actually end up substituting for dx before you substitute for like the original u, which is a little weird, but not that weird. So sine of 5x is u to the 7th du. We're going to reverse the power rule. So we get 1/5. It becomes 1/8 u to the 8th plus 1 times the reciprocal plus c. And then we can just finish this. So it'll be 1/40th, and then u is the sine of 5x. And then plus c. And there you go. All right, let's take a look at another problem. So some of these hopefully are starting to get, maybe you're just watching this for review and you're already really good at it. But, we kind of pick up a little bit of steam because we're just getting better at it, right? So I'm going to think in this one, I would initially pull out the 3 and not worry about it. Constant multiple, don't worry about it. The argument of the trig function is what you typically want to make u. It's a thing in parentheses, right? So I'm going to let u equal 5v minus 2. So the variable is v in this case. That's fine. So 1/5 du is dv. So we'll be able to sub for that. I'm going to pull out the 3 as a constant multiple and multiply by 1/5 because I'm pulling that out also. So 3/5 integral of sine of u du. Now you go through your list and you're like, the derivative of cosine is negative sine. So when I integrate sine, I'm going to get negative cosine. So when you integrate and get a co-function, you pick up a negative. So I'm going to get negative 3/5 cosine of u plus c. When you integrate and get a co-function, you pick up a negative. You got to memorize those derivatives. They're really, really helpful. I always think back to like, what is this the derivative of? Rather than what is the antiderivative of this, which feels backwards, but I mean, it's the way I do it and it works. So I'm going to get negative 3/5 cosine of substitute, get 5v minus 2, and then plus c. All right, let's see what the next one looks like. So we have the integral of the quantity 1 minus e to the 2x squared dx. All right, so what I'm going to do is I'm going to start this problem incorrectly to show you what happens, because this is a thing you do. You just like go with it, right? We've said typically you will make u equal things in parentheses, denominators, things in radicals. I have a thing in parentheses, so I'm going to try it. I'm going to say, so this won't work, but I'm going to say that u is equal to 1 minus e to the 2x. So if I do that, I will have that du is negative 2 e to the 2x dx. Look at what we have in the original. you don't have that e to the 2x just hanging around, right? Like you have 1 minus e to the 2x, but that's u. There isn't another e to the 2x. That's a problem. And because we don't have that, we can multiply in a number. That's not a problem. Constant multiples, because you can factor them in, factor them out, not a problem. We can't factor in a variable. And so this isn't the way to do it. We didn't match up our du and our dx. Not a problem. It just means we need to do it a different way. So what I'm going to do is I'm going to choose to expand. So we tried u-substitution. The method failed. We didn't fail doing the problem yet. The method is not the right method. So let's instead actually expand this. So square the first, multiply them together, gives you negative e to the 2x times 2, so negative 2 e to the 2x. And then square the last will give us e to the 4x. Now we just need to do each of these separately. You might choose to write this over as like 3 separate integrals. I don't think we really need to do that. I'm going to integrate 1 and get x because it's dx, so the variable is x, so 1 goes back to x. I'm going to, so I could do substitution here, but I know that I'm thinking of negative 2 as a constant multiple. The integral of e to the 2x, there should be a 2, so a 1/2. So I'm going to have negative 2 over 2 e to the 2x plus, there should be, I'm integrating e to the 4x. There should be a 4, so 1/4 e to the 4x, and then plus c. If you need to do u-substitution on that, do it. Don't be afraid. Don't let someone who's doing it in their head tell you like, oh, you don't need to do it. If you think you need to do it, just do it. You're better off getting it right, than whatever. And you can easily, well, semi-easily, you can go from this answer back to the previous row, right? The thing you took the derivative of just by quickly taking derivatives. So like that's a really good idea. I'm gonna clean this up. You can always check your answer by taking a derivative. Sometimes it's really onerous to take the derivative. That should say 4x. That should be e to the 4x, not e to the 2x. I'm not even gonna change it, but all right, I'll change it. How did I not notice that? I like reviewed this like a million times. So this should be a 4x. All right, so the tip here is sometimes you just have to expand and there's nothing that you can do about it. So don't worry about that. You tried u-substitution, it wasn't the right thing. You go back and you do it. Let's look at number 17. All right, integral of 6e to the 5x minus 1 over x minus 2 dx. This is a problem where if you're really confident, you might be able to do it in your head. So I'm going to do it in my head and explain what I'm doing. So integral of 6e to the 5x. 6 is a constant multiple. I don't really care about it. E to the 5x. There should have been a 5, so a 1/5. So now I have 6 over 5 from the 1/5 that I pulled out. And then it's just going to be e to the 5x. So I'll get 6 over 5, e to the 5x. And then this other one just looks like a natural log to me, so I'm going to go for it. Minus the natural log of the absolute value of x minus 2 plus c. So if that's what you're here for, that's the answer. Now I'm going to actually do the work, so you might choose to kind of skip this. I'm going to break this into 2 integrals, pull out the 6, constant multiple, and then minus the integral of 1 over x minus 2 dx. For the first one, I'm going to do a substitution. I'm integrating an exponential, so I'm going to let u equal the whole exponential. And then I'll find that du is 5e to the 5x dx. Divide through by 5. And I, again, get that perfect thing where I'm integrating du. That's what is going to happen. So this is 6, 1/5, the integral of du. I don't remember if I integrate this or not. Yeah, I'm going to integrate this right now. 6/5 u, which is 6/5, and then u is e to the 5x. All right, let's deal with the other one. I already use u, so I'm going to use w and let w equal x minus 2. So dw is dx. So our integral becomes minus the integral of dw over w, and that is perfectly a natural log, but we're not going to forget the absolute value, and plus c, and then we just sub back in for w. And there we go. So we did it in our head if you are into that. If you're not into that, you just show the work. It's not really a big deal. Pretty straightforward. Let's take a look at number 18. Integral of x squared quantity 4x cubed minus 5 all to the 8th and then dx. So again, typically you want to let u equal the highest powered thing in parentheses. In this case, both of those are the same. So I'm going to let u equal 4x cubed minus 5. So then du is going to be 12x squared dx, or 1/12 du is x squared dx. So it's often the case that dx has like another function with it, and they're usually in the original integrand, not next to each other. But you can see we have x squared dx, here's your x squared, here's your dx. We're subbing for those, so that's going to be 1/12 du. Pull out the 1/12, constant multiple, and then we're just left with the integral of u to the 8th du. Reverse the power rule. So 1/12, then it'll be 1/9 u to the 9th, and then plus c. And then 12 times 9 is 108. So 1 over 108, and then u, which is 4x cubed minus 5, to the 9th plus c. Perfect. So that's an example where, we tried to do u-substitution and it worked. On that maybe one or two problems ago, we tried to do u-substitution. It just wasn't the right thing. Doesn't mean you're wrong, just means you're using the wrong technique. Let's try the next one. Integral of 5 cosecant squared of 2x minus 3 dx. So to successfully do this problem, we're going to have to remember one thing for sure, and that is the derivatives of the trig functions. Memorize those so that you can recognize them to do antiderivatives. The derivative of cotan is negative cosecant squared. So we're actually in good shape because cosecant squared, we know what's going to happen. That's going to become negative cotan. It's just a question of like what's happening with u. So I'm going to write this as a couple of integrals. This step's really optional. You don't have to do this. And then I'm going to leave the 3 from that integral inside instead of pulling it out and doing the integral of dx. Because honestly, it kind of confuses me to integrate dx sometimes, but 3 dx I'm never confused about. So I leave it because it makes my life easier. We're going to have to do u-substitution on the first one. U is 2x. So 1/2 du is dx. So our integral will become 5 1/2 the integral of cosecant squared of u du. And then minus, let's just integrate it, right? 3x plus c. So for the integral that remains, we'll have 5/2. And then the integral of cosecant squared is negative cotan of u. If you integrate and get a co-function, you pick up a negative sign along the way. So negative cotan of u, and then minus 3x plus c, and then we substitute for u, which is 2x. So we get negative 5/2, I don't know what I'm saying, negative 5/2 cotan of 2x minus 3x plus c. All right, I'm going to do one more, and then I'm going to take another break. I think you can hear my voice struggling. All right, we're doing the integral of the 6th root of 1 minus 5x dx. Let me tell you, rational exponents are way better than radicals. You do not want to be messing with radicals when you're doing derivatives or antiderivatives. I immediately change them to rational exponents. So I'm going to rewrite this thing as 1 minus 5x to the 1/6 dx. So you can reverse the power rule, right? Like, how do you reverse the power rule on a radical? Like, what are even the rules there? But once we write it as a rational exponent, we're good to go. This is a straight u-substitution problem now. So u is 1 minus 5x, which makes negative 1/5 du equal dx, because du equals negative 5 dx. We do our substitutions. So we're pulling out the negative 1/5. We get u to the 1/6 du. And then plus 1 times the reciprocal will give us, so plus 1 is 7/6, so it'll be negative 1/5 times 6 over 7, and then u to the 7/6 plus c, and then that's negative 6 over 35. U is equal to 1 minus 5x, and then to the 7/6 plus c. Okay, I'm taking a break. It doesn't matter to you, but again, if I come back and sound different, you'll kind of know why. So I'm hitting pause right here. All right, no time passed for you, but I am back, and let's take a look at problem number 21. So we're going to do the integral of cosecant of 4t, cotan of 4t, dt. So you memorized all of the derivatives of the trig functions. That's really important if you're going to do these types of problems. This problem is actually almost exactly identical to the second problem, I guess, that we did, or the first or second. The derivative of cosecant is negative cosecant cotan. Therefore, I am not afraid to integrate this thing because I look at it and I think like, oh, that's one of the derivatives. Then I just go through the list in my head of the derivatives and I realize this is the derivative of cosecant. So I'm going to let u equal 4t. As you can see, I've already done. So 1/4 du is dt, and we're going to go for it. So we're going to make our substitutions. 1/4 integral of cosecant of u, cotan of u, du. And again, you might already be doing this in your head, and that's totally fine. I'm just showing all of the work. You know, for the people out there who are a little shy about doing it in their head or not sure about it or whatever, I'm showing that you can do the work and get the answers. Like, obviously, but who knows? The integral of, if we end up with a co-function, we pick up a negative sign. So it's going to be negative cosecant of u, and then plus c, and then we'll just make it negative 1/4 cosecant of 4t and plus c. So again, remember, the co-functions pick up a negative as you go through these. Let's do another one. So now you're starting to see a little bit of repetition here, and that's good because when you go to take the AP exam, you hopefully have done so many practice problems that every problem you're looking at feels repetitious, feels like something you've already done before. That's good, that's ideal. So this to me looks like things that we've done separately and together already. Let's do it. So I'm going to rewrite it as a couple of integrals, so pull out the 30 and just get dt over t plus 5. I'm going to pull out the negative 45 and then get e to the negative 3 dt. I'm going to do two different substitutions here. So for the first integral, I'm going to let u equal 2t plus 5. So 1/2 du is dt. And we can make our substitutions. So I'm going to have 30 and then 1/2 because of du. So 1/2 integral du over u, which is our goal, right? That's definitely natural log. And because we've done a bunch of them, it looks like natural log. For the next one, I'm going to let w equal e to the negative 3t. So dw is chain rule, negative 3e to the negative 3t dt, which means negative 1/3 dw is e to the negative 3t dt. And we're like ready to make substitutions, right? So it'll be, because it's an exponential, we let u equal, or well, w in this case, be the exponential. You end up integrating just the exponential. If everything works out for you, that should happen. So negative 45 will have negative 1/3 and then the integral of dw. All right, so for the first one, I'm going to get 15 natural log, because it's just 1 over u du, natural log of the absolute value of u, putting that in red because it's really important. And then for the second one, we'll have negative 45 times negative 1/3 is positive 15. And then the integral of dw is w because the variable is w, and that's what dw is telling you. And then plus c. And then at the next step, we'll just substitute in for u and for w. So we do have to keep track of that, but like not the worst thing in the world. And so here's our answer. Let me just point out, like, x squared plus 2 is definitely positive, but I'm going to leave the absolute value. And, whoa, where did that go? The reason that I'm leaving the absolute value is, why is this not showing up? I have, like, a thing. Oh, I don't have a thing. What did I even just say? Oh, I just, like, never mind. I'm, like, jumping ahead. Because obviously I write this out ahead of time, and then I'm, like, I'm doing the problem again as I, like, work through it with you. I had already like scrolled to the next problem and I'm like answering the wrong thing. So here we go. Let's go to the next one. It's been a long video. We're going to do the integral of the square root of 3x minus x over x squared plus 2 dx. This is a classic where like break it up and deal with each one separately because each one independently is not as hard as both of them together. So I'm going to kind of rewrite this thing. Radical 3x I don't like. I'd rather have it be radical 3 times x to the 1/2. Just because like I think it's a little clearer and I'm going to be able to reverse the power rule and that's like a good deal. So this will become radical 3 plus 1 times the reciprocal. So 1/2 plus 1 is 3/2. So 2/3 and then x to the 3/2. And then minus, all right, I'm going to do u-substitution on this. Like, so when in doubt, u-substitution. The denominator in this case, I'm going to let you be u. So x squared plus 2, which means that du is 2x dx, or 1/2 du is x dx. And we have x dx, so this is perfect. If we didn't have x dx, this would just be the wrong approach. And we would try something else. I don't know what else we would try in this case because this is the right approach. But we have 1/2 to use x dx. We can substitute for x dx, so I'm going to do that. Because remember, you really substitute for dx first. So it's 1/2, and then we'll get du over u. That's a natural log because we're hopefully starting to like recognize these things. So 2 root 3 over 3 is fine. X to the 3/2 minus 1/2. Natural log absolute value of u. Never going to forget the absolute value. It's like plus c is the most annoying thing for students to forget. The absolute value around the argument of a natural log is like way up there. So we're done. We just need to substitute back in. And then I will say the thing that I tried to say at the end of the last problem and messed up because I realized that I was looking at the next problem already. So we have the absolute value of x squared plus 2. X squared plus 2 is greater than 0. So you don't technically need the absolute value. I am going to leave it because having it there doesn't hurt anything. And if I did need it and I didn't put it, that would be really bad. So I'm leaving the absolute value. I am aware that it doesn't need to be there. If you check this on a calculator, it won't be there because like, why would it be? It's not necessary, but I'm gonna leave it. All right, next problem. Integral of x cubed minus 3x dx. So what happens here is I was just going through old AP exams, looking at problems that were on them, and then writing sort of like similar problems. So this is probably the beginning of another test, I guess. So we're just going to reverse the power rule on this and not make a big deal about it. Plus 1 times the reciprocal, and then -3 is a constant multiple, so -3 plus 1 times the reciprocal gives me -3/2 x squared plus 2. X squared plus 2. What? No, x squared plus c. And there you go. Don't make it more difficult than it needs to be. Let's move on to the next one. That was the best problem that we've done so far. Not really, but like I could use the mental break in the middle here. All right, integral of x squared plus x minus 2 over x minus 3 dx. So we've seen the reciprocal of this kind of thing a couple of times, and it's like kind of worked out to natural log, potentially. In this case, the numerator is a higher degree than the denominator. This is the first time we've run into this. This is the first time we've run into this entire concept. If the degree of the numerator is greater than or equal to the degree of the denominator, you should divide and then integrate. So this is one of the like big algebraic skills that they expect you to have, to be able to do long division and to recognize when to do it. So I'm going to do long division. You can actually do synthetic on this, but I think more people will remember long division. So I'm going to do that. So I'm doing the division. So x minus 3. And then x squared plus x minus 2 goes like, I say in the house. I don't know. Been a long time since I taught division. I'm aware that I kind of put these in the wrong place, but like what do I need to multiply x by to get x squared is x. And then I multiply, I get x squared minus 3x. I throw parentheses around the whole thing, subtract. So x squared minus x squared, gone, which means we did it right. X minus -3 is plus 3, so it's going to be 4x. Bring down the -2. What do I need to multiply x by to get 4x is plus 4. I'm going to multiply it. I get 4x minus 12. Parentheses around the whole thing. 4x minus 4x is gone, which means I did it right. And then -2 plus 12 is 10. All right, so the integrand becomes x plus 4 and then plus 10 over x minus 3. So that's actually what we're going to integrate. So if the degree of the numerator is greater than or equal to the degree of the denominator, first divide, then integrate. You got to keep that in mind. I mean, you're taking an AP exam. I mean, it's not going to be the easiest thing in the world, and there's like a lot of things to remember. This is one of the weirder ones for integrals. And then we can definitely integrate x plus 4. By the way, after doing the division, the most common mistake I see people make is they forget the like x plus 4. They forget the quotient. They just do the remainder. Don't do that. So I'm going to integrate x plus 4 and just get 1/2 x squared plus 4x. Then we can do a u-substitution on this, but I think that we're probably at the point where we can just say 10 is a constant multiple, and then 1 over x minus 3 is perfect. So I'm going to say it's 10 natural log absolute value of x minus 3 plus c. If you need to do the substitution, do it. I'm going to say that every single time. There's no reason not to show the work if that's what you want to do. All right. Integral of natural log of x over x dx. So it's not really obvious what to pick for u here if you are picking a u, except, like, why would you make u equal x? That doesn't feel like it's going to work no matter what. So it feels like I'm just going to have to go with natural log of x. And in general, when you're not sure, just pick something and find du and see if it worked, right? So if I had picked x, then du would be dx, and I still have this natural log hanging around. That's kind of problematic. So instead, I'm going to say u is natural log of x and see what happens. So du is 1 over x dx. And this turns out to be fine because that x in the denominator is also in the denominator of our du, right? So we actually have 1 over x dx is du. This is actually perfect. So natural log is u, and then dx over x is du, and we can just integrate. So I'm going to reverse the power rule, get 1/2 u to the second plus c, and then sub back in. This always looks a little weird, like raising natural log to a power. I have opinions about that, but now's not the time. I think you should write like the same as you do with trig, right? Sine squared of x. I think this should be natural log squared of x. That would look so much better. But for whatever reason, we don't usually do it, or ever do it, really. All right, next up. This looks like something we know how to do, right? You don't freak out. You pick something in parentheses, the thing to the highest power. I'm going to let u equal x cubed plus 3. And then just hope that the rest of the integrand gets combined into du. Like it has to, if it's going to work. So you get du is 3x squared dx, so 1/3 du is x squared dx. And so we're looking, there's an x squared and a dx in the integrand and for du, so we're good to go. So I'm going to pull out the 1/3 and just get the integral of u to the 11th du. Plus 1 times the reciprocal. So we're reversing the power rule. 1/12 u to the 12th plus c. And then 1/3 times 1/12 is 1 over 36. U is x cubed plus 3 to the 12th. And then plus c. And there you go. So hopefully these are getting like very familiar, because when you're going into the exam, you want to be very confident using u-substitution, which, if you've noticed, is most of what we're doing. Like, there have been some tips and tricks and things to memorize, but mostly we're just reversing u-substitution. Reversing the power rule, I guess I should say. We're using u-substitution and then reversing the power rule. That's what we're doing. All right, 28. Integral of x squared over the 4th root of x minus 3, x cubed minus 2 dx. I clearly need another break soon. All right, let's see. So I'm going to rewrite the integral because I don't like the way it looks. I don't like radicals. I don't like that thing in the denominator. I'm going to rewrite it as, instead of the 4th root of x cubed minus 2 in the denominator, I'm going to bring it up as x cubed minus 2 to the negative 1/4. So rational exponents are the way to go. And then I'm going to let the thing in parentheses be u, because I think it's going to work. So let's try it. So x cubed minus 2. So 1/3 du is going to be x squared dx. And then we look at our integrand and see if we have x squared dx. We need an x squared and a dx, but we have an x squared and a dx. They're almost never next to each other, but as long as it's a product, that does not matter, because we could rearrange it however we feel like. So we're going to sub for that. So I'm going to pull out the 1/3, constant multiple. Integral of, I get u to the negative 1/4. And remember, x squared dx is du. I mean, with the 1/3, but we already pulled that out. So we're going to reverse the power rule, plus 1 times the reciprocal. So negative 1/4 plus 1 is 3/4. So the reciprocal is 4/3. And then u to the 3/4 plus c. So this will give us 4/9. U is x cubed minus 2. And then plus c. All right, nice. Let's take a look. I'm going to try to make it to 30, then take a break. All right, integral of e to the x over 3 plus pi dx. All right, so you might be able to do it in your head. If so, great. Otherwise, I am just going to do a substitution. I'm not going to write it as two separate things because I know the integral of pi dx is just pi x plus c. So I'm going to say that u is really equal to, okay, apparently I'm just doing it in my head instead. So e to the x over 3, like the derivative of that is 1/3 e to the x over 3. So there should be a 1/3. So I balance that out with a 3 on the outside, and I get 3 e to the x over 3. The integral of pi is pi x, because dx is telling us the variable is x, then plus c. What I really did when I did it in my head was I did u is equal to e to the x over 3, and du is 1/3 e to the x over 3 dx. 3 du is e to the x over 3 dx, blah, 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 right? So I didn't show the work there. I thought I was going to, but I didn't. Here we go, number 30. So we're going to integrate 3 minus 4 sine of 2x dx. I'm going to immediately just rewrite this as two integrals. You don't strictly need that, because the integral of 3 dx is just 3x. Like, you could knock that out right away. Pull out the constant multiple, because I'm going to do that every time. Now, the integral of 3 dx is just 3x. Then we have minus 4. U-substitution, we'll let u equal 2x. And then 1/2 du is dx. So I can sub for that. So I'll get 1/2 the integral of sine of u du. When you integrate and get a cofunction, so I'm going through the list in my head of the derivatives of the trig functions. I see sine, I think, oh, the derivative of cosine is negative sine. So to integrate, I'm going to pick up a negative. So it's going to be 3x minus 2, and then I pick up a negative, so it'll be negative. Every time you get a cofunction, you pick up a negative. Negative cosine of u plus c, and then we sub back in. All right, I'm going to do one more before I take a break. Let's see. Integral of 3 plus 5e to the 2 minus x dx. I'm going to break this into two integrals because that's kind of what we're doing here, right? We're going to deal with 3 dx, which is just 3x again. And then we'll deal with this other thing. So let's separate it out. 3 dx plus 5 is a constant multiple. Integral of e to the 2 minus x dx. All right, first one, just 3x. And then plus 5 times this integral we need to do. It's an exponential, let u equal the whole thing. So u is e to the 2 minus x. Don't forget the chain rule here. Du is negative e to the 2 minus x dx. So negative du is e to the 2 minus x dx. So our integral becomes, I'm going to pull out a -1, integral of du. And again, always that will happen. If you're integrating an exponential, you let u equal the exponential, you always end up integrating just du. It's kind of like magical. I mean, you can see the work and why it happens, but it feels magical. So let's finish this. 3x minus 5, the integral of du is u plus c, and then we substitute back in. We get 3x minus 5 e to the 2 minus x plus c. All right, I'm going to take a break. You won't even notice it, but I'm just letting you know in case I sound different. Hopefully I sound better. I feel like I'm losing my voice over time here. All right, I'm back, and let's take a look at the next problem. So this is the integral of 5 over 6x plus 18 dx. This should hopefully feel like a natural log to you. Like, I look at this and I'm like, oh, we have a constant over a linear thing. This is going to give us a natural log. So I'm going to let u equal the denominator, which means 1/6 du is equal to dx. And we're just going to do the substitution. So 5 is a constant multiple, so I'll pull that out. Then 1/6 integral of du over u. And this will give us, the only thing you could possibly mess up here is forgetting the absolute value. But we're not going to do that, right? So we get this plus c, and then we sub back in. So I would have my answer look like this. Certainly on a free response question, for sure. I will warn you that on a multiple choice question, it is entirely possible that this answer could look very different because of properties of natural logs. So I'm just going to throw it up on the screen here. This could happen. So you could have taken a 5 over 6 out to begin with, right? Because 6x plus 18, there's a common 6 there. So I take out 5, 6, and then I have to integrate 1 over x plus 3, which just gives me the natural log of the absolute value of x plus 3. So we could have that answer. The reason for that, you can see below in green, is the property of natural logs that natural log of a times b is the natural log of a plus the natural log of b. And then the natural log of 3 is just a number. So natural log of 3 plus c is just some new c value. So I called it c2 down there. But just be aware that that could have what did I do here? I took out 3 when I was supposed to take out 6. So my work there is wrong. It should have been 6 times the quantity x plus 3, natural log of 6 plus the natural log of x plus 3. But the idea still holds, so I'm not going to change that. But that's what it should have been. That's the reason that these are the same. Plus c does a lot of work for you sometimes. All right, let's take a look at the next one. Integral of quantity x to the 5th minus 3 to the 2/3. So I see something in parentheses, so I'm thinking that's probably going to be u. And then x to the 4th dx. I'm going to not worry about the x to the 4th because I'm hoping that it'll just be a part of du. So let's say u is equal to x to the 5th minus 3. So then 1/5 du will be x to the 4th dx, or du is 5x to the 4th dx and then divide by 5. So we get to this. Let's do, so I mean, it did happen, right? And this is something that like you can kind of take for granted that it will happen, especially at like the Calc AB, Calc BC level. Like it kind of has to work, or you would need to know more techniques of integration than you currently know. So I have an x to the 4th dx. That's going to be 1/5 du. So I'm pulling out 1/5. And it'll be the integral of u to the 2/3 du. Going to be plus 1 times the reciprocal. So 1/5. 2/3 plus 1 is 5/3. So 3/5 u to the 5/3 plus c. And then 3 times 3, 1, what am I saying? 1/5 times 3/5. You probably shouldn't do like 70 minutes of calculus in a row where you're just talking it through because it all starts to muddle together. Hopefully you're not just cramming right before the exam. I know a lot of you probably are, but better to do this in pieces along the way. I should have been recording this video for like weeks instead of doing it all on a Saturday morning, but what are you going to do? All right, so I get 3 over 25 quantity x to the 5th minus 3 to the 5/3 plus c. That's our answer. All right, we are on to number 34. Let's see what it looks like. Integral of x e to the 4x squared. So I'm not afraid of that because that's an exponential. I'm just going to let u equal the exponential. And then minus cosine of 3x, which I'm also not afraid of because I memorized the derivatives of the trig function, so I am familiar with that. So I'm going to split this into 2 integrals and then kind of do a u substitution and a w substitution because I'm doing 2 different things. So we get our first integral and then minus our second integral. The first integral is integral of an exponential. Let u equal the exponential. So u is e to the 4x squared. And like at this point, I'm really confident that that x dx situation is going to happen. Like it has to. So du is e to the 4x squared times 8x dx. So chain rule is a big deal when you're finding du. Got to get good at derivatives so you can get good at antiderivatives. Maybe you saw that coming. I don't know, but it's definitely true. All right, so 1/8 du is going to be x e to the 4x squared dx, which should be the entire integrand. That happens every time you do this if it's going to work. And you can see that it is. So we're just going to get 1/8 the integral of du because 1/8 du is x e to the 4x squared dx. Perfect. Now for our second one, I'm going to let u equal 3x or w equal 3x because we're doing a second substitution. That just keeps your work cleaner to use different values there. Some people don't do it. Probably I don't really do it when I'm not making videos, but you should do it just to like clean up your work. So 1/3 dw is dx. Do our substitutions. So pull out the 1/3, cosine of w dw. The integral of 1/8 du is 1/8 u. So it's really important that you keep track of the variables here. The integral of du is u. The integral of dw would just be w, but we're not integrating that. We're integrating cosine of w. So I look through my mental list of derivatives of trig functions. The derivative of sine is cosine, so this is good. It's going to be minus 1/3, and then just sine of w, and plus c. And then we do, we sub back in, right? We sub for u, and we sub for w, and we write our answer. So here, I don't know why I didn't just go straight through there. All right, this, and plus c. All right, let's see what the 35th question looks like. The 35th question doesn't look terrible, but it's the integral of the quantity root x minus x over 3 all squared dx. So you might think to yourself, like, should I just do u-substitution on this and make u equal the whole thing in parentheses? You can kind of quickly work out that if you do that, like du is going to look nuts, right? Because the derivative of x to the 1/2 is 1/2 x to the negative 1/2. The derivative of x over 3 is negative 1/3. There would have to be a lot of extra stuff hanging around if you could just let u equal radical x minus x over 3. That's not going to work, which means we're in that scenario again where sometimes you just have to expand. And they like to do this in multiple choice questions where they kind of like give you this other fake option as an answer. Like the fake option would just be 1/3 this thing to the third and be like, oh, this person doesn't know how u-substitution really works because they didn't match du. We're going to match du, so we know we have to expand this. So here goes. Radical x squared, so you square the first thing, radical x squared is x. You multiply them together, so root x times x over 3. I'm thinking of root x as x to the 1/2. So root x times x to the, times x over 3, sorry, should be x to the 3/2 over 3. So square the first term, multiply them together, which is x to the 3/2 over 3, times 2. So we're going to get minus 2/3 x to the 3/2, and then square the last. I'm really just doing like a plus b squared, but I'm running through it for you because that radical x is like a weird thing to have. Now we're just straight up reversing the power rule, like all the way through. Plus 1 times the reciprocal. So x will give us 1/2 x squared. If you, so minus 2/3. If you add 1 to 3/2, you get 5/2. So it'll be minus 2/3 times 2/5, and then x to the 5/2. And then we have x squared plus 1 times the reciprocal is 1/3 x cubed. And 1/3 times 1/9 is 1 over 27. So I'm going to write that as x cubed over 27. Generally, I don't like writing that for whatever reason. I actually prefer to write 1 over 27 and then x cubed. So when I simplify this thing, I'm probably going to do that. So 1/2 x squared. It's like I feel like you should have all of your exponents in all your variables in numerators or none of your variables in numerators. And so what I've chosen here, instead of, I did 1/2 x squared, so I want to do 1 over 27 x cubed. That's just looks. There's nothing to do with the answer there, but whatever. All right, number 36. Integral of pi over 12 cosine of pi over 3 times x dx. Straight up u substitution. I'm going to let u equal the thing in parentheses, the argument of the trig function. So this one's a little weird because of the pi's that are involved. Don't let that scare you. Just like do the work. And if you end up with pi in a numerator, fine. If it's in a denominator, fine. Like, doesn't make a difference. So du is pi over 3 dx, which means 3 over pi du is equal to dx. That's fine. So in the original integral, the pi over 12 is a constant multiple, so I'm going to pull that out. Then for dx, we're going to do 3 over pi du. I'm going to pull out the 3 over pi. Integral of cosine of u. And then we already subbed for dx, so the du. All right, and then I think of my list of derivatives. I know the derivative of sine is cosine, so this is good. So pi over 12 times 3 over pi is just 1 over 4. Right, the pi's cancel, and then 3 over 12 is 1/4. And then we will get sine of u plus c. And then u was pi over 3x. Not a bad problem, right? So don't freak out about things, because once you've really got a handle on u-substitution, you know that u-substitution is going to handle like the challenging, weird multiple things. and the rest of it's just going to kind of work out. All right, 37. Integral of dt over the quantity t minus 27 to the 2/3. I don't like that in the denominator, so I'm going to bring it up into the numerator. So I'm going to rewrite this before I even start. And even when I do them in my head, I basically rewrite them that way. Because how else are you going to do it? How are you going to reverse the power rule when the thing is in the denominator? It doesn't make any sense. All right, I'm going to let u be the thing in parentheses. So u is t minus 27. This is like the best case scenario where du is literally just dx, or in this case dt. So we can just substitute here. We get u to the negative 2/3 du plus 1 times the reciprocal is going to be 3u to the 1/3 plus c, and then we sub back in. That problem was delightful. Could do. I mean, I don't want to do too many more problems, but I could do a lot more of that. All right, number 38 it is. So 38 is the integral of the quantity 1/10 times the quantity 2 plus h cubed squared. So it's the whole quantity. The 1/10 is inside that quantity, and then we're squaring that, and then dh. So h is our variable. I'm going to just expand this, right? This is one where we've seen a couple of times where like just letting u equal the thing in parentheses doesn't seem to work, especially if there's nothing outside of the parentheses, because how would our du ever match up with anything? So we're going to expand. 1/10 squared is 1 over 100. So I'm going to pull that out as a constant multiple. Now I have to square the quantity 2 plus h cubed. So square the first, you get 4. Multiply them together, you get 2h cubed times 2. So we'll get 4h cubed. And then square the last, you get h to the 6th. dh. Now it's all reversing the power rule. So the 1 over 100 just, stays. The variable is h, so the integral of 4 is 4h. And then 4h cubed, I'm going to write it as, I'm just going to reverse the power rule and not worry about the coefficients. So I'm going to say it's 4 over 4h to the 4th. I know that's just h to the 4th. And then 1/7 h to the 7th. And then plus c. And then because I think you would do this, I'm going to distribute the 1 over 100, but also this problem is done, especially from a free response standpoint, but I'm going to do it. So 4 over 100 is 1 over 25 h. 1 h, so h to the 4th divided by 100 is 1 over 100 h to the 4th. And then 1/7 times 1 over 100 is 1 over 700. And then h to the 7th, and then plus c. And that's it. So weird problem. Why is that 1/10 there? Who knows? But it is. Number 39. Okay, so we're going to do the integral of dx over x squared plus 6x plus 25. I look at this, and I think, and I'm often asked, how do I decide what to do? I kind of don't decide what to do. I just start doing the things that are most common, and then next most common, and then next most common. So the order of my thoughts on this problem are, perhaps I can just reverse u-substitution, right? I really reverse the power rule. I don't know why I confuse the power rule and u-substitution apparently. I really want to reverse the power rule. That would be my dream here. So I would try to let u equal the denominator, x squared plus 6x plus 25. But then du would be 2x plus 6 dx, and I do not have that. So that can't be right. Right? So my next thought is oh, maybe it's a natural log. So that's also basically eliminated at this point. But I always think am I just reversing the power rule? Is it a natural log? This is when I have a rational function, right? When there's, in particular, quadratic in the denominator. Is it reversing the power rule? Is it a natural log? If it is none of those, I tend to think it is arctan. It's probably arctan. Arctan is always kind of lurking around, waiting to be there. But in this case, it's not obviously arctan. Frequently with arctan, we have to complete the square. So how do you know to complete the square? None of the other things have worked, which means it must be arctan, so you have to complete the square. So I'm actually going to do that on this. So to complete the square here, what I do is I write down x squared plus 6x. I leave a gap. That's where I'm going to complete the square, and then I write the plus 25. To complete the square, you take the coefficient, and I have plenty of videos on completing the square if you don't remember this, but I take the coefficient of x, which is 6. I divide it by 2 to get 3. I square that to get 9, and I'm going to add that and subtract it. So plus 9 minus 9. When you do that, the first 3 things will be your perfect square. You have completed the square. So that's going to give me the quantity x plus 3 squared. And then negative 9 plus 25 is just 16. So I've completed the square, which means I can rewrite the integral. Instead of having the quadratic in the denominator, I'm going to put this completed square in the denominator, which is also quadratic, but like not what anyone means. All right, so we get dx. Also, because I am thinking this is arctan, right? I should have put a thing here. You've got to memorize the derivative of arctan. The derivative of arctan is 1 over 1 plus x squared. 1 over 1 plus x squared. That 1 is crucial, but that's why I've rearranged this. Instead of doing the quantity squared plus 16, I made it 16 plus the quantity squared. I always want it to look the same. So that's what we have. So what I'm going to do here is, because I want the 1, I'm looking for 1 over 1 plus u squared, basically. I'm going to divide everything I see by 16 to get a 1 in the bottom left corner. I have a separate video where I just do integrals that end up with arctan. I definitely recommend you check that out because people do struggle with this a little bit. You don't need to, right? You just have to remember the derivative of arctan is 1 over 1 plus x squared. It's that 1 in the bottom left of the fraction that is the key to unlocking arctan problems. So I've created that, right? I'm going to take out the 1/16 from the numerator. And then I just have dx over 1, which is the crucial thing. And then this is x plus 3 squared over 16. 16 is a perfect square, but even if it wasn't, I'm going to rewrite this as the quantity x plus 3 over 4 all squared. And the reason I'm doing that is I'm now going to do a u-substitution because I have 1 over 1 plus u squared. That's what I want. So u is equal to x plus 3 over 4. If you don't recognize that you're dealing with arctan problems are like impossible because you just don't see what to do. And it's not really anyone's fault. It's just like when you're so far in the woods that you can't figure it out, you're probably dealing with arctan. You got to remember that derivative. So 4 du is equal to dx. Let's make our substitution. So the 1 over 16th, and then I'm pulling out a 4, so I'm going to have 4 over 16, integral of du over 1 plus u squared. I kind of regret that du is not purple, but it's not, so whatever. So this is 1/4, because 4 over 16. And then 1 over 1 plus u squared is arctan. Like the integral of 1 over 1 plus u squared is arctan of u all the time. So here we're getting arctan of u, and then plus c. And then we just substitute back in. So we get 1 over 4, arctan of x plus 3 over 4, and then plus c. Arctan is a lurker, right? So you first think you're going to reverse it. I keep writing u-substitution, and it drives me insane. You're trying to reverse the power rule. Reversing the power rule doesn't work out after you do your u-substitutions. You're like, maybe it's just a natural log. It's not a natural log because our problem was really du. It's not that we can't like figure out what u is. It's du cannot match up. At that point, I'm thinking definitely arctan, especially because of the quadratic. You might have to complete the square. So there's 2 very algebraic things that they expect you to know. One of them is long division, which we did a couple of, right? That's if the degree of the numerator is greater than or equal to the denominator. The other one is completing the square and then integrating. Completing the square and then integrating is almost always going to give you arctan. I think in the next one you'll see frequently arctan and natural log kind of come together as like a thing. But let's see, I'm just going to write it down. So if you have just a quadratic in the denominator, you should immediately think this is probably arctan and try completing the square and see how it goes. So practice completing the square, look for quadratics in the denominator, you should be good to go. Let's look at number 40, which is the last problem that I have prepared here. And kind of looks like u-substitution might just work on this thing. If I try to do u-substitution, I would let u be the denominator. So u is equal to x squared minus 2x plus 2. Du then would end up being 2x minus 2. And if you look at the numerator, I cannot make that work. Like if I had x minus 2, I could create, no, if I had x minus 1 rather, I could create 2x minus 2. But as it is, I have x plus 3. So my initial guess of u substitution and then trying to reverse the power rule is not going to work. I can't match up du. So I can't be reversing the power rule, and it can't be a natural log because I can't match du. This is where you think this must be arctan. If it's arctan, I'm going to have to complete the square. So I'm going to say that I'm completing the square in the denominator. X squared minus 2x, leave the gap, plus 2. I take the coefficient of x, which is negative 2, divide by 2 to get negative 1, square it to get positive 1, add that, and subtract it. So we have this. The first three things will be your perfect square. So that's the quantity x minus 1 squared. And then negative 1 plus 2 is just 1. So now we're going to rewrite our integral. So I get x plus 3 over 1 plus x minus 1 squared dx. All right, where do we go from here? From here, what I'm going to do is I'm going to say that u is equal to x minus 1. Right? Because I'm thinking it's arctan. Arctan is 1 over 1 plus u squared. U should be x minus 1. This is a challenging problem. I think this is actually probably a little more challenging than you would see on the AP exam, but it definitely happens. I mean, it could happen. So I'm thinking arctan, which means it should be 1 over 1 plus u squared. U should equal x minus 1. Let's see what happens. So du is dx. Not a problem. The problem is this x in the numerator. Like, we don't have 1 over 1 plus u squared. We have a bunch of stuff over 1 plus u squared. So I need to substitute for that x. Like, I can substitute for x minus 1. It's going to be u. I can substitute for dx. It's going to be du. I need to sub for that x. So I'm going to say, based on this, x is actually just u plus 1. So let's do that. Let's substitute u plus 1 for that x. So we will get u plus 1 plus 3 over 1 plus u squared, and then du. All right, this is coming together. So we'll have u plus 4 over 1 plus u squared du. Now, I need to break this up into two separate integrals. So the way that I know to do that, experience. Like if I let w equal the whole denominator, 1 plus u squared, then I would just get 2u du, and I have this plus 4. I'm going to break it up into multiple integrals. Probably if I was doing this video again, which like 90 minutes later, I'm definitely not, I might have left this problem off. This seems a little too challenging for the actual AP exam. Not for an AP class though, and certainly not for like a Calc 1 or Calc 2 class, but probably for an AP exam. This is a little beyond what you would be expected to do. All right, but I've broken it up into two, and now you can kind of see the first integral looks like it's going to work if we do a w substitution. I'm going to let w equal 1 plus u squared. So remember, the whole thing started thinking of arctan, and suddenly it looks like a natural log has snuck in here. So 1/2 dw is equal to du. I'm sorry, u du. And if you look, we have u du, right? We have u over 1 plus u squared du. U du is a thing, so I can make this 1/2 the integral of dw over w. That's natural log for sure. The other integral is integral of 1 over 1 plus u squared. Perfect arctan. So it's going to be 4 and then arctan or tan inverse of u plus c. Now we just need to sub back in. Well, we need to do the first integral actually, I guess. 1/2 natural log absolute value of w, and then plus 4 tan inverse. I'm just going to sub for u here. U is equal to x minus 1, right? So x minus 1, and then plus c. We still need to substitute for w. So w is actually kind of interesting. So w, we know, is 1 plus u squared. But we know that u is the quantity x minus 1. So we really have 1 plus the quantity x minus 1 squared, which is this. But that is our original denominator. So we can actually just go back to x squared minus 2x plus 2. So, I mean, I like that we're ending on this problem because it's a really interesting problem. It kind of combines a lot of ideas. And if you've done every other problem and really understand them, I think this is definitely an achievable problem. I do think it's a little harder than the AP exam would throw at you. I don't know, on the BC exam, maybe. I doubt it, but maybe. But it does illustrate, like, you can get natural logs and arctans at the same time. it shows you when to think of arctan, right? Like you initially were like, I'll just let u be the denominator. But then du doesn't work out. So when u is the denominator and du doesn't work out, probably you're dealing with arctan. You got to complete the square, make your substitution, and go from there. Anyway, that is 40 integrals, antiderivatives. All of them, except maybe this last one, are definitely just inspired by actual problems on the AP exam. You got to know how to do all of them. So memorize those derivatives you need to know, memorize the antiderivatives you need to know, do a lot of practice. I hope you found this helpful, and good luck.